Hello, everyone. My name is Eric Hong. I'm a Senior Director of Engineering at Mixel Incorporation. First, I would like to thank Samsung Foundry to give us an opportunity to present today. The title of my talk is Leveraging FDSOI Technology for MIPI Application. Benefit of FDSOI versus bulk silicon. FDSOI is an acronym for Fully Depleted Silicon on Insulator. Here's the agenda for today. I want to provide a brief overview of Mixel Incorporation and the MIPI Alliance before diving straight into the benefit of FDSOI versus bulk silicon technology. I will then highlight a bit about Mixel's IP in FDSOI and provide a use case from our partner NXP Semiconductors. NXP was able to achieve very impressive power efficiency on their ultra-low power application processor. Lastly, I'll wrap up with some concluding thought and references. A quick introduction to Mixel Incorporation. We are industry leader in interface mixing IP. The company has been around for over 20 years with a focus on MIPI application since 2006. Mixel specialized in MIPI PHY and was the first silicon IP provider to demonstrate silicon-proven D-PHY, C-PHY, and M-PHY. We provide a completely integrated solution including PHY controller and platform with many silicon-proven IPs in Samsung Foundry. Our mantra is first time success is the rule, no exception. And this track record is true for Samsung Foundry as well. This slide shows our 3 generation of D-PHY test chip for the data rate of 1 gig, 1.5, and 2.5 gigabit per second. The first test chip for D-PHY we did was back in 2008. We were able to achieve very wide TXI opening and excellent RX performance with ample timing margin from all of these test chips. MIPI started in mobile phone market and since then rapidly expanding and gaining wider adoption into such applications as automotive, IoT sensor, VR, AR, MR, and other consumer electronics. MIPI PHY is ideal for low power, high bandwidth, and minimum area. Mixel's strength is in MIPI PHY, camera, and display interfaces. I'll now talk about benefit of FDSOI versus bulk silicon. Body bias capability of FDSOI facilitate changing VT of transistor dynamically. For bulk technology, the ability to do body biasing is very limited due to parasitic current leakage through bulk. Body biasing gives a powerful knob to lower power consumption, boost performance, reduce silicon area, and improve yield. I'll also cover benefit of intrinsic FDSOI process due to differentiated transistor structure from bulk technology. Lastly, I'll talk about how analog performance and area are improved through FDSOI process. Body biasing is a very powerful feature. With FDSOI process, you have dual gate structure where independent voltage can be applied to body to raise or lower VT of transistor up to a couple hundred millivolt. Reverse body bias can be applied to raise VT to lower leakage current. This is extremely important for application requiring ultra-low power consumption. On the other hand, forward body bias can be used to lower VT, thus significantly boost performance. The left diagram shows the cross-section of NMOS and PMOS in FDSOI process and how body bias is applied to either lower or raise VT. With FDSOI technology, VT can also be adjusted by flipping well, as shown in the bottom diagram. The total power consumption consists of 2 components. First, there's a dynamic power, which is capacitance times VDD squared times frequency. The second component is the leakage current. In conventional bulk technology, DVS, which stands for dynamic voltage scaling, is used to dynamically adjust supply voltage based on workload and operating condition to improve power efficiency. In FDSOI technology, you have dual knob of DVS and body biasing to further reduce power consumption. Body biasing allows trade-off between dynamic and leakage power to achieve lowest power consumption for a given workload and operating condition. Through forward body biasing, FDSOI chip is able to operate at low voltage than bulk silicon while maintaining at the same level of performance. The left curve shows energy efficiency achieved through DVS alone, DVS in conjunction with body biasing. As you can see, body biasing further improves power efficiency substantially. Here's a slide on how leakage current can be reduced through reverse body biasing. For IoT and wearable application, most of time is spent in standby mode with short bursts of intensive performance. Therefore, standby power has much bigger impact on overall power consumption and battery life. The left curve showed dramatic reduction in leakage current for different reverse body bias voltages. In this example, with maximum reverse body bias of -3 volt, you can see 50x reduction in standby power consumption. In bulk technology, as channel lengths scale down, you need very complex channel and halo doping to suppress short channel effect. Unfortunately, it leads to increased gate-induced drain leakage and increased device variability. This is why you often see exponential increase in leakage current for fast corner in bulk technology. Also, because of deeper junction, drain-induced barrier lowering effect makes very hard to turn off transistor when drain voltage is high. In FDSOI, typically channel is undoped or dopant usage is greatly reduced. So gate-induced drain leakage and variability is substantially reduced. In addition, because of ultra-shallow junction, drain-induced barrier lowering effect is greatly reduced as well. Lastly, barrier oxide prevent any leakage between source drain and bulk. This slide shows how performance can be boosted through forward body biasing. Forward body biasing lower VTO transistor and lead to higher gate overdrive and increase ID set. FDSOI enable so-called turbo mode or burst mode through forward body biasing while operating circuit at optimal energy point. For example, forward body biasing allows operating chip with lower supply while maintaining same level of performance. So overall active power can be reduced by reducing dynamic power consumption despite increase in leakage current. The left curve show that for 0.5 volt, 550% performance boost is achieved through forward body biasing. And with the higher supply, you see 34 to 60% performance boost. In FDSOI process, a gate control is greatly enhanced through ultra-thin channel, leading to very steep subthreshold swing. For a given I-off target, FDSOI has a lower VT than bulk technology, thus you end up with a higher gate overdrive and ID set. This is another example of how FDSOI improves performance through its intrinsic process. Here's how junction capacitance compare between bulk and FDSOI process. In FDSOI, source and drain junction to capacitance to bulk are completely eliminated through buried oxide. As a result, 90% reduction in junction cap is reported. Lower source drain junction cap improve the speed of a high-speed circuit and reduce dynamic power. Here's a slide on how yield can be improved through body biasing. Body biasing can help further reduce die-to-die variation for speed and leakage current. The left curves show that some of the slow part fail to meet required speed. In this case, forward body bias can be used to boost the speed of this fail slow part, so this slow part can be recovered. On the other hand, there is typically maximum power limit for a given package type. So you could also end up with yield loss or excessive leakage and power consumption. So in this case, reverse body bias can be used to reduce leakage current. So this fast part with excessive leakage can be recovered. As you know, yield improvement translating to cost saving. I have talked about how FDSOI help improve PPA of digital application. Now I'll switch gear to talking about how analog design can also be benefit from FDSOI process. FDSOI improve analog gain and matching or reduce active area while maintaining same level of matching. Device matching is very important role, plays a very important role in designing high precision analog circuit. Lastly, I'll talk about how higher bandwidth can be achieved through FDSOI process. Let's look at how analog gain compare between 28 FDSOI and 28 bulk technology. FDSOI has much higher transconductance because ultra-thin body allows superb gate control. The bottom curve shows significantly higher transconductance for FDSOI process. In FDSOI process, short channel effect is greatly reduced because of ultra-shallow junction, and it leads to much higher output impedance compared to bulk technology. The top curve shows huge improvement in analog gain for FDSOI process. Matching is very critical for designing high precision analog circuit. Typical analog design practice to reduce mismatch is to upsize WL of transistor and or increase gate overdrive. Increasing WL leads to increase in analog area. So as mentioned previously, variability is greatly reduced for FDSOI process due to limited usage of dopant and increased gate overdrive. The left curve shows standard deviation of VT comparison between bulk and FDSOI process. The horizontal axis is a device channel length, and vertical channel is a parameter called AVT, which is a process-dependent parameter. Lower AVT means VT variability is reduced with same W and L. As you can see in the left plot, VT variability is much smaller with the FDSOI process. Or you can significantly reduce W and L, achieve same level of matching as a bulk for FDSOI. This slide shows how spur bandwidth of analog circuit is achieved for FDSOI. FT and i.MX are key figure of merit used as a benchmark for high frequency performance of transistor. FT and i.MX are proportional to transconductance and inversely proportional to capacitance. For FDSOI, higher FT and i.MX is achieved through higher intrinsic transconductance and the boost in transconductance through forward body biasing and lower gate and source drain junction capacitance. For PHY and SerDes application, higher FT at max enable extending the maximum data rate. FT at max performance of 20 FDSOI is comparable to 16 or 14 FinFET technology. There is a substantial cost saving of using FDSOI, since FDSOI is a much simpler process than complex 3D FinFET technology. I'll now walk through evaluation we have done to quantify power saving and reduction of active area through forward body biasing. In this example, we use a simple digital circuit, and we minimize device sizes while maintaining same speed for DT corner by applying maximum forward body biasing. Next, I'll present the result of our evaluation. We normalize power and speed of SS and FF corner to DT corner here. And here are normalized results with no body biasing and maximum body biasing. From this evaluation, we saw active area reduction of 55% through 4 body biasing. For TT corner, power saving is 50%. For TT corner, power saving is 14%. Through 4 biasing, both active transistor area and power consumption are reduced while slightly improving performance for slope corner. Here's a list of silicon-proven Mixel IP in 20 FDSOI and Samsung Foundry. We have our MIPI PHY universal at 2.5 gigabit per second per lane with DSQ and full loopback testability. I also want to highlight that D-PHY DSI TX is the IP integrated into NXP's i.MX UAP processor, which I will discuss in more detail shortly. We currently have several IP planned for Samsung Foundry, including the D-PHY version 2.5, which is the latest D-PHY standard, MIPI D-PHY standard that support up to 4.5 gigabit per second per lane. We have several different D-PHY configurations available. Universal D-PHY is a superset containing all block for TX and RX. And TX and RX PHYs are fully optimized for power and area. We also have TX Plus and RX Plus configuration, which allow on-chip loopback suitable for mass production testing. In TX Plus and RX Plus configuration, we implemented very compact loopback receiver and transmitter, so our TX Plus and RX Plus PHYs have very small area and power overhead. We have a novel and patented implementation on RX Plus, which allows full speed loopback regardless of external loading from ATE. Our PHY consists of hard macro and CIL. For CIL, we typically provide as RTL. This slide shows the picture of our Samsung 20 FDSOI test chip with a universal D-PHY IP. On the right, we have a very wide TXIA diagram at 1 gigabit per second. Next, I will talk about use case from our partner NXP on how they were able to achieve very impressive power efficiency. NXP's i.MX 7UAP processor deliver better user experience and lower energy consumption across all types of product and ideal for very demanding long battery life application. Power efficiency was improved through several different ways. First of all, NXP chose the right process technology. Samsung 20 FDSOI technology enabled tuning silicon for lower power or performance. Secondly, with heterogeneous architecture, NXP was able to power gate as much silicon as possible for least amount of leakage. There were multiple power modes implemented like run, low power run, standby, or deep state mode. Each of these power modes were optimized for optimal power efficiency. Lastly, IP selection like power efficient Mixel's MIPI PHY IP was very crucial for further improving power efficiency. NXP's i.MX 7UAP enable ultra-low power, secure and portable devices, and power devices for home control, wearable, portable healthcare, portable printing, game accessory, general embedded control, and IoT edge application. i.MX 7UAP application processor extend battery life to its fullest. Here's a very impressive power efficiency improvement result from i.MX 7UAP processor over previous generation products. As you can see here, 5 to 20x reduction in standby power and 2 to 6x reduction in runtime power. Here's an example of smartwatch system level design based on i.MX 7UAP processor. Mixel's DSI TX D-PHY IP was integrated into this application processor and drive touchscreen. Here's a summary of my talk. There are many compelling benefits with FDSOI technology for power, performance, area, and yield improvement over bulk technology. The differentiated body biasing feature of FDSOI provide efficient trade-off between power and performance and drastically reduce standby current to prolong battery life. Mixel has successfully developed chip first-time silicon success on more than 10 IPs on multiple FDSOI process nodes. NXP has worked closely with Mixel on understanding market demand to deliver right mix of features and power capability within the FDSOI process technology. This collaboration resulted in i.MX ultra-low power family of application processor, achieve 5 to 20x reduction in standby power and 2 to 6x runtime power efficiency improvement over previous product. Here are some of the references used in my presentation. We have a virtual booth here at Samsung Foundry event. I would like to invite you to come and visit our virtual booth. Thank you very much for listening to my talk, and thanks Samsung Foundry and our partner NXP for the collaboration and providing us with great materials. I hope all of you and your family are staying safe and healthy during this challenging time.